We're going to test a kits and parts wideband RF amplifier circuit today. I've assembled the board, so what we'll do next is we'll apply an RF input and we'll measure the output, and we can calculate the gain then. We'll do this a couple of different ways. Okay, we're all ready to start. Our signal generator I've got set to 14 megahertz and it's putting out 20 millivolts RMS. Now, you don't usually want to trust these unless you send them to the Cal Lab all the time, which this hasn't been to the Cal Lab for a long time. So what we're going to do is just verify what it says by checking it with the oscilloscope. Looking at the oscilloscope, we can see that we have 10 millivolts per division in the upper left corner. Sweep speed there is 100 nanoseconds. We have about 4.8 divisions of waveform displayed. Now that's peak to peak, and we put in 20 millivolts RMS. So the way to convert peak to RMS is you divide the peak to peak by 2 to get it to peak, and then once we do that we multiply it by 0.707 to get to RMS. So if we take 4.8 times 10 millivolts is 48 millivolts, divide that by 2, we get 24 millivolts. We multiply that by 0.707 and we get 16.96. So we get almost 17 displayed on the scope. The generator says we're 20, so we'll just live with what the scope says, so it looks like things are in relative agreement. I've added the output to the amplifier on the screen now. This is the input, this is the output. Input's at 20 millivolts per division. Output down here is at 200 millivolts per division. We have about 4.2 divisions of output. If we multiply that times 200 millivolts, that'll give us 840 millivolts output peak to peak. So we'll convert that to peak by dividing by 2. That'll give us 420 millivolts. Then to convert peak to RMS, we'll multiply it times 0.707, and that gives us 297 millivolts. So we put 20 millivolts in and we're getting 297 millivolts out. There's a rough rule of thumb you can use, well it's not rough, it's exact, for certain values of dB. When we're talking about voltage, every 6 dB causes a doubling of voltage, or if you're attenuating, it causes make it go to 1/2. So 6 dB is times 2 or times 0.5, depending on whether you're amplifying or attenuating. And 20 dB is a factor of 10, either 10 times as much or 1/10. So we can see where we put 20 millivolts in and we got 297 out. That's more than a factor of 10 by a little bit, so we have at least 20 dB of gain out of the amplifier. So if we calculate that all out, we can take the formula for dB for voltage is 20 times the log of voltage 1 divided by voltage 2. So we had voltage 1 divided by voltage 2. We have 297 millivolts divided by 20 millivolts. That gives you 1.1171. I'm not doing this in my head. Trust me, I can't do that. I calculated it out and wrote it down. So I've got 1.1171 and I multiply that times 20 and that gives us an amplifier gain of 23 dB. And that's right around what they spec this amplifier to give. Okay, I know the math was a little difficult. You lost your slide rule, haven't used it for so long you can't do logs anymore. don't have a calculator, haven't been to school for 50 years, there's plenty of excuses why you don't want to do it that way. Especially if you got nicer equipment. This may be old, but it works great. What we're seeing here is on the spectrum analyzer is the 14 megahertz signal that I'm going to input into the amplifier. So if I take and hook that signal into the amplifier, each division on the screen at this point is equal to 10 dB. So we should gain 10 couple divisions, and we can just measure it right off the screen. We don't have to do any of the calculation. So let's switch the output of the generator to the amplifier and the output of the amplifier into the spectrum analyzer. We've made the switch, and if your memory works for you, you remember that we started right here. This is what the input to the amplifier was, so we've got 10 dB, 20 dB, about 3 more dB there, so it looks like we got about 23 dB of gain through the amplifier. That's two different ways you could do it. Another way would be with a power meter. Unfortunately, my power meter is broken right now, so I can't demonstrate that method, so we'll just have to live with these two. So I'm confident to say that my particular amplifier anyway at 14 megahertz put out 23 dB. You go, wait a minute, all his information on his website uses 7 megahertz, 40 meters. I'm sorry, I'm a 20 meter fan, so anything I build is going to work on 20 meters. One other interesting test we could do is a sweep test, or a frequency response test. What I'm showing here is I'm sweeping between DC basically on the left hand side of the screen and 100 megahertz on the right hand side of the screen. So each division is worth approximately 10 megahertz. So if we look, here's our 10 megahertz, 20 megahertz, 30 megahertz, 40 megahertz. So we're pretty good at 40 megahertz or so. That may look pretty drastic as far as the dip between here and up here, but remember, on voltage, 6 dB is half voltage, so that's actually probably less, somewhere around 6 dB at this area here. You probably won't be using this amplifier up around 100 megahertz, so we can decrease the upper frequency response, and we'll take it down to 50 megahertz, and it looks a lot nicer. So that's between about 0 and 50 megahertz there. So this amplifier would be real usable on any of the HF bands. We can come on down. There's 20 megahertz. Up here, there's 28. That's not bad. So we can go to 30. Between 0 and 30 and be pretty good. Remember, we had 23 dB of gain, so if we lost 6 dB, we'd still end up with 17 dB of gain. So if you want an inexpensive RF amplifier, the kit for this, including all the parts, was $8. You can go to kitsandparts.com and take a look at a lot of his other boards he has also. Very few places you can buy a building block module for $8, including the printed circuit board and all the parts, plus all the directions. You can look at the board layouts and the schematics on the website also. You need to order one, build it, and begin having fun of your own.